Hi, let's learn something new again. There are several good programs for creating photogrammetry, reality capture and photoscan, which is now called Metashape. Photogrammetry is a very cheap and convenient way to create 3D models from photographs. Nowadays there are iPads with built-in LiDAR that can quickly scan a room, but they're still expensive. However, they are also very convenient. These models can be extracted and used in tracking. But to this day, the primary working tool of an on-set supervisor is still a camera. This is very convenient and inexpensive. When you're on set, you photograph literally everything. Then you feed all these images into a photogrammetry program, which generates geometry. And you can use this geometry in tracking. This can all be done literally in just a few clicks. In other words, it would be a sin not to use such a tool. So if you're on set, always take a series of photos and build photogrammetry from them. Use it in tracking. Everything can be very easily exported as an OBJ file. Also, based on measurements, you can specify point coordinates, scales, and all the things we've been talking about this whole time. You can refine the model created with photogrammetry in the same program or in some external software. Or you might not refine it at all. Either way, everything can be exported as an OBJ file and brought into 3DEqualizer as regular geometry. The geometry simply snaps into place. Let's turn off the image plane. View. The Show Image Plane option refers to that white plane. We haven't loaded a shot yet, but even when we do, it will usually just get in the way in 3D space. None. Here we see only the 3D model. You can even apply a texture using UV mapping. Let's enable texture projection onto the polygons. We can turn on the polygons and, for example, turn off the lines. And here in Equalizer we have the model reconstructed from photogrammetry, which we can use for tracking. Let's load the shot. Let's start from frame 101 and export the buffer compression file. Set the sensor size. What do we know about this shot? Let's assume we don't know the focal length, but we can clearly see that this is a zoom shot, meaning it's not a camera movement, but a lens zoom. What can we do with this? Let's simply track this shot using the photogrammetry and then calculate the zoom. Everything as usual. We'll track a few points. There's a very strong motion blur. Let's expand the pattern area to accommodate it. Ideally, we would track more than one object, but since during the zoom there's very little to latch onto, and the whole image is heavily blurred, we'll work with what we have, tracking the object that remains stable in the frame. We have 4 persistent trackers for geometry-based tracking. That's generally enough for the software to determine the root frames and build the main camera movement. But only if we know the coordinates of these points, otherwise we would need more. Fortunately, we have geometry. Go to lineup controls and while holding shift, start moving the camera. Also, since no point is set yet, moving the camera isn't very convenient. In lineup it moves almost uncontrollably. So first we can assign coordinates to one point and rotate the camera around it. We haven't set the focal length yet. First, because it changes, and second, because we don't know it. Right now we focus not on how well the geometry fits the image, but on aligning specific points to their corresponding locations on the geometry. The camera's field of view in the project currently differs from what it was during filming. We can select a point. Press Extract Vertex and snap it to this location. We can toggle the geometry on and off if it interferes with viewing the image. For this, use the 3D Models button or the M hotkey. I select the next point and enable the model display. And I align it with one of the vertices on the model. And I do the same with the other points. We select a point, choose Extract Vertex, and assign its coordinates. It's almost in position now. Extract Vertex. Now, if we toggle the model display on and off, we can see that the camera is already roughly in the same position as it was during filming, except the focal length is still incorrect. Overall, we're almost in the right spot. It's worth adding trackers not only in the center of the frame but also closer to the edges. However, since parts of the image go out of frame, we'll track only the visible areas. Switch back to manual tracking, select for example this corner, and track it as long as it remains visible or until strong motion blur starts. Go back one frame and close the tracker. Take this spot. Also track it as long as it continues to track successfully. And we also assign coordinates to them using the geometry. Go to Lineup Controls, enable the geometry, and find the spot on the geometry that corresponds to the location we tracked. Extract Vertex. Or, if there's no vertex at that specific spot, you can use Extract Polygon. Next point. Extract Vertex. One more point. Extract Vertex. And we can place another point at the top of the frame, again using manual tracking. We track it as long as it holds, then stop. Now we go to Lineup Controls. We assign the point to correspond to the vertex coordinates. We know that the camera is stationary. We can specify this right away. Camera constraints. Fixed camera position constraints. And that's basically it for now. Next, to calculate the shot, we need to specify the focal length. In the curve editor, we have many parameters, from camera position and rotation to distortions, including the focal length curves. We can either manually set the focal length values on different frames and adjust them later, or calculate the entire curve automatically. Doing it manually depends on how much information we have. For example, we know that from frame 1 to 10, the focal length stays constant, starts changing around frames 11 to 21 to 22, and after frame 122 remains unchanged again. All of this can be drawn directly on the graph manually. If we know the focal length, everything becomes much easier. For example, we can specify that in this frame, the value is around 18 millimeters. For instance, I know that an 18 to 55 millimeter lens was used here, and the zoom goes from 18 to 55 millimeters. If you're not sure that a key is placed accurately, you can edit it, just like we did in the deviation browser. Go to the menu, Edit, Edit Curve Keys. Position X, the frame number for example, 111. Position Y, the focal length value, but for some reason, divided by 10, it is shown here as 1.8. Okay. Next we move to the frame where the focal length adjustment ends. We set a new key, either manually by moving the point on the graph or through the menu. Edit, Edit Curve Keys, where you can enter the desired values. Both methods work. Choose whichever is more convenient. Frame 121, 55 millimeters. And now we can try to solve this camera. Apply. Alright, one thing we forgot. We didn't specify that this is a dynamic zoom, meaning the focal length isn't taken from the lens parameters, but instead is an animated curve. Just like we previously set up dynamic focus distance, here we need to enable dynamic zoom. And solve. Camera. By toggling the geometry display on and off, you can check how well everything aligns and see how accurately it fits. We haven't used lens distortion yet and set the zoom by eye, but even so, everything aligns quite well. When playing back, you can see that it doesn't align perfectly. That's because we set the zoom manually, almost by eye. For a rough pass, this is enough, but we'll refine it a bit further, although honestly it's already fitting quite well. If we have at least an approximate idea of how the zoom changes within the shot, we can adjust it. If not, we can try calculating it from scratch. Both options are done in the same panel, so you can come there either with some preliminary result or with nothing at all. But before that, it's essential to finish the tracking and at least roughly know the frame range within the shot where the zoom change occurs. We go to the calc menu, zoom curve, calculate zoom curve. And here we have this panel. What's in it? What settings? Mode of operation. This is the working mode. We choose what we want to do, calculate from scratch, compute the zoom curve from 0, fine-tune existing curve, adjust an already existing one. Depending on this choice, the parameter block below is either enabled or disabled. This block controls the behavior of the curve's motion. If you haven't set it yet, the equalizer will try to calculate it automatically. But if you are fine-tuning an existing curve, the initial calculation is no longer needed. If we calculate from scratch, we can choose the type of focal length change. Options are increase, ramp up, decrease, ramp down, V-shape change, down up, first decrease then increase, or vice versa, up down. In our case, if we were calculating from scratch, we would select ramp up since the focal length is increasing. Next, we choose the number of curves, meaning how many distinct zoom movements occur in this shot. Next is the sampling density. If the zoom changes unevenly with jerks or jumps, it's better to set curve type to high. For smooth, uniform zoom, low or regular works fine. Parameters. Complexity determines how twisted the curve can be. For abrupt movements or fine oscillations, increase this value. Smoothing controls how smooth the curve will be. For jerky motion, lower smoothing to preserve details. For smooth motion, increase it. First curve. Located between frames defines the frame range where the zoom change starts. Last curve located between frames defines the frame range where it ends. In this case, first curve, approximately frames 110 to 112. Last curve, approximately frames 119 to 121. Also, if you know approximately the starting and ending focal lengths, you can specify them. If not, you can leave the full range. For example, right now it will search from 10 mm to 67 mm, which generally fits the range of our 18 to 55 mm lens. The only thing is, we know it definitely doesn't start at 67 mm. We can specify roughly where it starts and ends. Here are the values we entered, including the intermediate ones. That's it for now. We can just note that we're fine-tuning. Let's go ahead and calculate with what we have. We can see how the curve has been calculated. In the deviation browser, you can observe the approximate error. Click Use Zoom Curve to transfer the curve into the curve editor. When we recalculate the camera, unlike the position and rotation values of the camera and objects, this curve does not get reset. Calc all from scratch. We can see that everything aligns quite well at the beginning, but towards the end it can be fine-tuned slightly, since there are still few points. I'll add one more tracker. Here's a high contrast point. During the focal length change, I can't precisely indicate where it is, so I pause the track and resume it at the point where I can see the tracker again. And in lineup mode, I also set its coordinates. I enable the model and use extract vertex. If you load the grids, it will be even more precise. If we switch to 3D orientation mode, we can see here is our camera. And this is the spot where the focus changes. We can delete the focus pull curve and try to calculate it completely from scratch. That is, we've reset all the values. Go to calc zoom curve. With fine tune, we switch to calculate curve from scratch. The same ranges are still entered, but let's reset them and see how the calculation goes. Essentially, we've only set the curve shape, meaning the focus is changing from a lower value to a higher one. All other ranges have been reset. Let's see how it calculates. And here we can see that even with this calculation, everything is computed fairly accurately. This is partly because the shot isn't very complex, but that's how it works. Click Use Zoom Curve. Let's check the ranges where the values are now. 18 and 53. Solve the camera. Apply. Go to Line Up. And we can see that overall everything fits. The curve graph can be adjusted manually without fear or fine-tuned through the same panel. You can also adjust it together with distortion. Here you can select one of the distortion parameters to refine in combination with zoom. For now, however, we're not going into the parameter adjustment window, but back to the Calc Zoom panel. We switch to fine-tune to adjust the existing zoom curve. Enhance convergence. This enables a more precise but slower calculation. Reduce peaks in deviation curve means that in areas where the deviation browser shows spikes, the solver will adjust the zoom to reduce those peaks. And we enable adjust for the static lens distortion parameter we selected. Now, along with the other parameters, this distortion value will also be optimized. Again, the more parameters you include, the slower the calculation, which is why I chose only one. We enable the adjustment. Here we can see that the error spikes in the deviation browser have disappeared and the final phase has been slightly corrected. Use zoom curve. And apply. And that's how we set up the camera, even if it's static, and track using photogrammetry while calculating the zoom. Again, it's much easier when you have geometry because when the coordinates of points are known, the software can much more easily determine whether they are in the correct place at the current zoom. If the coordinates still need to be calculated, the software has more freedom, which reduces the chances of hitting the correct values accurately. Thank you for watching and see ya. Have a good solve.